That's interesting. All right, so let's get started with this. Has anybody got any solutions or any questions or anything about the homework? You have a solution? Or any troubles? Okay, good. But it's kind of hard to say when it says graphically, right? So you can't really give the answer. So what I got was a picture that looks like this. I hope I got it right. Can anybody confirm or dispute? One of the constraints, this constraint, I then want you to be in this half plane. Second constraint, want you to be in this half plane, and also want non-negativity. So where they intersect, you would see, I didn't draw it, but here you'd get the intersection, but they're all negative in X2, so there are really no feasible solutions. Does that look like yours? Yeah. The dual is simple. Because there are two constraints, there are two decision variables in the dual, and as always, the right-hand sides become the objective coefficients. The objective coefficients become the right-hand sides. Maximize changes into minimize. Signs flip round, and the coefficients get transposed. So this is the dual problem. And when you plot the dual problem, what I got was this picture. So the two constraints give me the feasible region, which is unbounded, and if and the objective function goes in that direction. But if you go along this line, then the objective function keeps growing, and there is no bound on the bound on it. Is that similar again to yours? Okay, good. So might have got it right. Okay. So this illustrates one of the situations where we have an infeasible primal but an unbounded dual, and we know that one of the possibilities. But an infeasible, we couldn't have a bounded and feasible dual in this case. And then the second example, well, there are strategies to find primal and dual which are both infeasible, I think. Right, so yeah, how would you go about something like that? Well, I don't know. I've created an example like this, but there are, of course, many different solutions. Again, one thing when you're trying to come up with something like this is that if you want them both to be infeasible, then the objectives don't matter at all, because no matter what objective, if it's infeasible, then it's infeasible, and that's that. Fair enough. So you just come up with some constraints, ignore the objective, and then you have to get the transposition and ignore the objective, and then you put your right-hand side to such a way that you wouldn't get any feasible solution, and you put your right-hand side here so you wouldn't get any feasible solution, and the objective will then be determined by these right-hand sides and this objective by those right-hand sides, but you don't care about the objective. So that's a strategy. Okay. I didn't do the plots, so it's only a half-baked solution. Any questions about these homework problems? No? Okay, so well, I promised you that we would be doing, what did I promise you? Kind of post-optimality analysis questions, where we solve a problem, and then we decide, and then we try to understand what happens when we start changing some of the parameters. So like some of the coefficients in the constraints, or some of the numbers in the objective, or some of the right-hand sides and things like that, and what's going to happen to the optimal solution. But before we started kind of started with that, yes? Pardon?
2. Is it homework out of 2?
Homework out of 2, yeah. Where was I? Yeah, we kind of started last week because what we said was that the dual optimal solution gives you some kind of value of the resources you're using. So in other words, if you change the right-hand sides in the constraints, then the dual optimal solution will tell you how how the objective is going to change. Okay, but don't worry if you don't remember, because we're going to do that a bit more properly later. But before we get there, we want one important technique, which is called dual pivoting. And dual pivoting is used in situations like this, but it's also used in when you change the constraints, for example, and it turns out that the solution you had as optimal solution is no longer feasible, and you use dual pivoting to get the new optimal solution, as we will see later. But first, let's start what it is. So let's say you get a linear programming problem like this. Now, what is interesting about it is that these right-hand sides are greater than, these inequalities are the wrong way, as it were. Right, so they go greater than or equal to. And last year, we learned what to do in such situations. Does anybody remember? Two-stage simplex. Does that ring a bell? Artificial variables, G-objective, all that stuff. So that's one way of dealing with these. But there is a different way, and maybe even better, which we will now have a look at. And the key there is to change all these signs. So what we really cared about last year was that we never get negative right-hand sides. Negative right-hand sides were a bad thing. Negative numbers in the val column were a really bad thing. And whenever I saw a negative value in the val column, I was very angry about your solution. But now we're going to do the opposite. So we don't care about negative values. So if we get a problem like this, what we're going to do first is convert the constraints that are going the wrong way into ones that are going in the right way, but have negative right-hand sides. Okay, so if I times this constraint by -1, I get this one, and if I times this constraint by -1, I get that one. And now, in this situation, I could just do what I'm used to, so add a slack variable 1, slack variable 2, slack variable 3, and get a tableau that looks like this. Okay. Now, what do I want to do here? So I get a tableau like this. And the problem was, as you have in your handout, it's to minimize. So I don't have, while minimizing, I want the objective row to have no positive numbers in it. And this objective row indeed has no positive numbers in it. So I could say I'm happy, problem solved. But the problem is not solved because I can't have negative values in the val. And so what we're going to do is do a pivot step. But in this case, the pivot step is not determined by the objective row, but it's determined by something nasty in the val. And nasty means negative. So negative is bad. And I could choose either the S1 row or the S2 row as my pivot row because they're both negative. But similarly to what we were doing, I just look for the thing that is most negative. So this is how I'm picking my pivot row. Okay. And in normal pivoting last year, how did we choose the pivot column?
Whichever ratio was lowest.
Whichever ratio is the lowest, with on the condition that we wanted the pivot element always to be positive. So we never considered any zeros or negative numbers for the pivot element in the column. And among the rest, among the positive ones, we did all the ratios of val and the pivot element. Whichever was lowest, we took it. Okay? Well, now, in this case, what we're going to do is something quite different. Now, the reason we didn't want the pivot element to be negative was that the pivot step, what it does, it divides the whole row by the pivot element in that first step. And if the pivot element was negative, then that would give us a negative value in the val, starting with a positive one. But now, it's quite the reverse. So we have a negative value, we want it to be positive, so all we're going to do is only consider the negative numbers in that row as possible pivot elements. So we have two possible pivot elements, this -3 and this -1. And just like before, we do the ratio test. Except in this case, we do the ratio test not of the val and the pivot, but of the Hodge entry and the possible pivot element. Okay, so what I'm doing is I'm looking at this -2 or this -1, and here I get -2 over -3, so that's 2 over 3, and here I get -1 over -1, so that's 1. And again, I picked the least ratio as we were used to. So the least among them is the 2/3, which indicates that this 3 should be the pivot element. Or -3 rather, sorry. Okay, so again, just very briefly to summarize how we get the pivot element in the dual pivot step, you look for a negative, possibly the most negative number in the row. That determines the row. And then among the negative entries in the row, we do the ratio test of the opt value with possible pivot element. We'll pick the least ratio by an absolute value if these were positive, but that's now let's just stick to negative entries. So we pick the least ratio, and that's how we find the pivot element. How do we do the pivot step? Well, we do the pivot step exactly the same way as the usual pivot step. So S2 in the basis would be replaced by X2 and S1 and S3 stay in the basis. And then as a reminder, you know that the X2, well, the second row is divided by the pivot element. So minus 6 divided by minus 3, we get 2. We get minus 1, 1, 1/3, 0, minus 1/3, and 0. Okay, this is just that row divided by minus 3. And now, of course, the goal is to get in the x2 column zeros by a suitable row reduction like this. So how do I get it? Well, got minus 1, I just add this one to get 0. So that means that I'm adding this new x2 row to the first row. So that's going to be a minus 1 there. And minus 4. 0, if I want it. Minus 2/3, 1, minus 1/3, 0. S3 should be 1, 2, 0, 2/3, 0, and 1/3, 1. And in the objective row, I'm getting 4, minus 5, 0, minus 1/3, 0, minus 2/3, 0. It's kind of what I'm supposed to get, I think. Any suggestions about this tableau? Is it any good?
No, still got minus as well.
Exactly, that's still a minus 1. So what would you propose?
Same thing again with that as bigger.
Yeah, that's quite right. So I've got a fresh copy. So again, need another pivot step. We need another pivot step. So that means that this minus 1 determines the pivot row. Well, what are the candidates? Minus 4, minus 2/3, minus 1/3. Which one of them is going to be the pivot element?
X1.
X1. I don't know. There's a 5/4 ratio, I think. This one, X3, has 1/2, and S2 has 2. Is that right? I think the least one is the 1/2. Means that this element is going to be the pivot element. So in the basis now we get X3, X2, and S3. So some bits of the tableau are clear. Now, if you did it properly, you would realize that, well, you find out that x3 has val 3/2, and x2 also has 3/2, and s3 has naught. And the objective is 9/2. And I'm not going to finish all the elements. So you have something to do on the bus home. But all the important ones I've written, the rest I'm leaving. So how about this tableau? Any good? Good. Why is that?
Vowels are all positive.
Vowels are all positive. How about the up row? Nothing positive, other than the actual objective. That looks good. Oh yeah, so that's nice. So this is the optimal solution then. Well, x1 is naught, and x2 is 3/2, and x3 is 3/2 as well. And the slack variables are all 0. And the objective is 9/2, so that's it. Okay, so a few remarks. So the first remark is, as a reminder of how we know that the tableau is the one we're looking for, we've just really said it, and it's the val must not be negative. And in the object, but ignoring this could be negative, or this could be whatever it wants, because that's the value of the objective, and we don't know what the optimal value of the objective is going to be. It could be positive or negative. So that we don't check, but we have to check that in the up row there is nothing positive in the case of a minimization problem, nothing negative in the case of a maximization problem. So because what we were solving was a minimization problem, this is good. That's remark number one. Remark number two is what does the ratio test do? What kind of job does it do? Why do we want to take the least ratio there? Yes. Come on.
Because we're on the on the graph, the lowest place where it's all the lines are true. That doesn't make sense.
Yeah, that was kind of the idea when we were doing the ratio test in the final thing. That's quite right. So that was the geometric idea. So the geometric idea was when we're pivoting, we want to stop when the first constraint becomes violated. That's where the first constraint going on here. That's right. What we made sure, though, in the primal pivoting was that we wouldn't get any negative values in the valve. And so this ratio test, kind of dually or transposively, if you like, makes sure that we don't get any positive values in the object. So we want to pick the least ratio because if we chose any of the other ones, we would get some positive values in the up row. standard is not such a big deal because that would just tell us to pivot to get optimality. So not like crime against humanity, but why do extra pivot steps when they're not necessary? So we just check the ratios, and that makes sure that we don't get any wrong signs. Okay. And the third question is, why is it called dual pivoting? Because pivoting is really the same as it has always been. The only way that it's different is how we select which is going to be the pivot, and the rest is block standard. But why is it called the dual pivot, or why is it called dual pivoting? Oh. Why is it called dual pivoting? Now, look at this. Let's write the dual of this. Okay, one thing, there is something that is slightly nasty about this, is that it's a minimization problem. So in a minimization problem, when we're doing the dual, we kind of find it useful to have all the signs going greater than or equal to. Is that how we're getting the dual normally? So because of that, we can rewrite this constraint by timesing it by -1, so we get minus x1, minus x2, minus x3. That's going to make our life easier. Greater than or equal to -3. And now we can write the dual in the standard way. So what is the dual? Is it to minimize or to maximize? Maximize, yeah. What's the objective?
It's 3, 6 minus 3.
Yeah, it's 3, 6 minus 3, but it should say y1, y2, y3, or whatever you want to call the dual variables. Usually we use x's and y's. They come from the right-hand side, so we have 3, 6, and -3. And then the constraints, I can't see. Well, the first constraint is 3 minus 3 and 1. No, 3 minus 3 and -1 after I times it by -1. Isn't that? So get 3, oops, wrong place. 3y1 minus 3y2 minus y3 should be less than or equal to 3. Do we all know what we're doing? So it's 3 minus 3 minus 1, and this 3 is coming from there. And the next constraint is then y1 plus 3y2 minus y3 is less than or equal to 2, and y1 plus y2 minus y3 is less than or equal to 1, and all the y's we want to be non-negative. Okay, that's the dual. So how would you solve a problem like this using the simplex method? Well, it looks very standard, doesn't it? Just a maximization problem, everything, all the constraints go the right way, things fine. So we get a tableau. Looks like this. How do you find the pivot element? We're maximizing here.
Use the most negative on the object row.
That's the -6. So that's the same -6 that was determining the pivot row before is now determining the pivot column. How would you find which of numbers in the pivot column is supposed to be the pivot element? Ratio test. But you're not looking at the -3, right? Final pivot step, we don't want the pivot element to be negative. So the ratios that I'm looking at are what? 2/3 and 1? Because I'm looking at this 2 and this 1 divided by this 3 and this 1. Do these ratios look like anything we've seen? Yeah. So now I don't want to do the pivot step, but the basis you would get would be S1, Y something, Y2, S3, and you get the gist of the idea. So I promise you that the val would be 5, 2/3, and 1/3. Value of the objective is 4, and the objective row is -1, 0, 1, 0. Okay, probably have a blood pressure problem or something. 1, 0, 2, 0. Right. So do these numbers also look familiar? When you look at the tableau we got after the first pivot step.
You're right.
Well, trying to be. I don't know, I'm feeling a bit faint. Anyway, can you see that these numbers are appearing in the previous tableau? So what we have in the objective row, previously we had in the val, and what we have in the val, we have in the objective row. Okay, there are some extra zeros, either way, but that's just the way it is because we need the zeros in some of the columns. Other than that, the numbers are the same. It's kind of what this means is that what we call the dual pivoting is really just like the usual standard pivoting in the dual problem, or in the dual LP. And that's why it's called dual pivoting. So there is a bit of a caveat perhaps. So sometimes you don't get the, well, yeah. Well, we had, when you look at the tableaus we had while doing the dual pivoting, they were all optimal in the sense that we had no positive numbers in the objective row. So it was really just dual pivoting. But then there are situations where you don't get either. So you might have some negative numbers in the val, and you might have some wrong signs in the objective row. And then it's not really dual pivoting. But what you can do is kind of, it's called, I don't really, I'll just change to the next slide, which gives a summary of dual pivoting. But there is this 2.1. So in 2.2, that's, well, just, okay, I should probably go through it. So the dual pivoting, as we've been doing it, we find the pivot row by looking for something negative in the val, as we did, and then we're looking for a negative entry because we want to pivot on a negative entry, and we do the ratio test. Now there is this note that if the wrong sign is present, then we should do pivot on one of those columns. It kind of doesn't matter which one we choose, but that's not strictly dual pivoting. So this would be some kind of, this is called like a primal dual pivoting, something like that. But don't think too much about that. Should be enough to understand that the dual pivoting works well when we have a problem which is, I call it optimal. The proper word for it is actually dual feasible. So no wrong signs in the objective row, and the val has the wrong signs. Whereas the primal pivoting, the usual pivoting, we have a primal feasible problem. So the vals are all the right signs, but the objective row has some wrong signs. And depending on which situations we're in, we either apply the dual pivot or the primal pivot. And that's kind of how you can solve any tableau to optimize it. Okay. If that's about enough on dual pivoting. Any questions?
Stuff that we did at the start was basically just a cheap way of changing it into y's, right?
Which one?
When we were choosing negative r.
Yeah, it's a cheap way of, it is in some sense a cheap way of creating the dual and then solving it and then going backwards. Yeah.
So it's like doing the same thing, but you don't actually have to create a dual.
Yeah, they're doing the same thing, but doing it in a transposed tableau. Yeah. That isn't exactly. Any other questions? No, so that's it for now, and then from next week on we'll be actually looking at what happens if we change the right hand side, what happens if we change the objective, what happens if we change some of the other things in there. Solving problems.